Hello everyone, my name is Nevrus Kaja, and today I will be presenting the paper from Leslie Lamport in ECE578 class, Advanced Operating System. The paper is called Time, Clocks, and the Ordering of Events in a Distributed System. The paper will provide us with algorithms on how to apply those concepts in a distributed system environment, which we all know is different from a normal computing environment or a local computing environment. Before jumping into paper details, I'd like to provide first some concepts regarding clock and time. Clock, as we all know, is a device for measuring time, while time gives sense to past, present, and future. Without time, we wouldn't be able to distinguish those three tenses. Now, clock in computing is the same concept as in real life. If we have an analogy with a human heart, like human heart has to beep in order for a human to be alive, also a clock has to tick in order for a computing system to continue operating. Now, what is time in a distributed system? Why do we need it? And does it really work? Well, in a distributed system, we also might need to know the time of the day at which an event happens in a specific computer, as we all have a lot of computers, and we need to know a particular event when it happens, whether it happened before or after another particular event. So we need to have, in order to accomplish this in a traditional environment, we have external clock synchronization. Now, for external clock synchronization, we will see that we have a lot of problems with transferring and time delays between different clocks in different computers, as this is a distributed system. Now, why do we need the time in a distributed system again? Well, we need to know for two events, how did those two events happen in relation to each other in two different computers in a distributed system environment. We might need to know the relation between them, when did they happen, what time interval, and how was their internal clock synchronization. Now, in order, as it's been done from until now, distributed systems or local systems, they use a physical clocks. What is a physical clock, though? Physical clock is a clock that it's an electronic device that counts oscillations in a crystal at a particular frequency. Now, every computer, as we said, contains a physical clock because in order for them to operate, they should be able to have this clock ticking. Now, count is typically the divided and stored in a computer register, while this value is time-stamped. It's a timestamp event in that computer. Two events will have different timestamps if clock resolutions is sufficiently small. If those two events happen in exactly the same time, then the timestamp of those two events will be the same. Now, many applications, though, in the distributed system environment or in also other environments are only interested in the order of events and are not interested when exactly or what time the event happened, but they are interested particularly if this event happened before another event or happened in the same time as this event. And now we're going to discuss physical clock in distributed systems. Well, does physical clock actually work in distributed systems? In order for it to work, we have to synchronize all clocks to some known high degree of accuracy, and then measure the time relative to each local process to determine order between the two events. So basically what we're seeing is that we have to have different physical clocks synchronized with each other in different computers in a distributed environment in order for us to understand when those events happen. Well, if we're going to follow this approach, we're going to see that we have some problems in implementing this, because it's very difficult to synchronize clocks in different systems that are distributed with each other, are not close to each other. Because crystal-based clocks, which are widely used in every computing system, that they tend to drift from each other. The drifting is sufficiently small, but it's also in the same time, it adds up on time, and then we will see that after some time this drift has become considerably high. Now, drift is small, as we said, but adds up over time. For quartz crystal times, typical drift rate is about 1 second every 10 to the power of 6 seconds, which this means 1 second of drifting in 11.6 days. So as we said, according to this slide, physical clocks are not a perfect solution to distributed systems. Now, Leslie Lamport in this paper introduces the idea of logical clocks while abandoning the idea of physical clocks. As we said before, in computing systems, we are only interested, or we're generally interested, only in the ordering of events, and we do not pay a lot of attention in whether the event happened exactly in what time it happened. So Lamport in 1978 wrote this paper, and he introduces the logical clocks, which handles the problem of clock drifts in a distributed system. He identifies the main function of a computer clocks while using the logical clock concept. And the main question that he answers on this paper is how to order events in a distributed system. And he indicates, or he provides, what clock condition must be satisfied in order for this ordering of events to happen in exactly the same way in all the other distributed systems, or in all other systems in a distributed environment. Now, ordering of events. Well, what is ordering of events? Ordering of events is basically a concept that tells us what event happened before or after another event. So what is the relationship between the execution of two events? Now, event ordering is linked with the concept of causality. What is causality? Causality is the relationship between the cause and effect. So it's in the same time the relationship between two events. For example, saying that event A happened before event B is the same that event A could have affected the outcome of event B. Because by the production or the output of event A might have some information that affects the input of event B. So that's why they have to be ordered, and we have to know the relationship between them. But if event A and B happen on processes that do not exchange any data, their exact ordering is not important and is outside of the scope of this paper, because if they do not exchange any data, or they do not have any relation between them, then we're not interested in seeing how this order happened. Now, Leslie Lamport introduces, in order to have a total ordering of all the processes in a distributed system, he introduces the relationship has happened before. The relationship has happened before must satisfy the following three conditions. If A and B are events in the same process, then A comes before B. And then this is shown by the following notation. Also, the second condition, if A is sending a message by a process and B is the recipient of another process, then A has happened before B, because A has to send the process and sometime has to pass through the transformation, and B has to receive that process. So we can say that if A is the sending process and B is the receiving process, then A has happened before B. Also, the third condition that we're going to take in here is that if A happened before B and B happened before C, then we can say that A happened before C. So those are the three conditions for the relation has happened before. Let us now introduce this relationship with an example. Now we had three conditions, and we have three processes, I, J, and K. The bold black line shows the timeline of each process and the events that happen in each process. So we can see that in process I, A and D happened. In process J, C and E has happened. In process K, B has happened. Now we are interested to see the relationship of those events between each other. Well, from the first condition, from the previous relationship, we can say that A happened before D, because we can obviously see that A happened before D in the timeline of a process I. We can also say that C happened before E in process J, from the second condition. Now, from the third condition, we can see that A sends a message to process J, and process J is the receiving of process I. Now, we can also say that A happened before E, because A is the sending process and C is the receiving process. So this event A happened before this event C, according to the third condition of the relationship. Now, the relationship has happened before, as we have described as of now. It cannot provide us a total ordering of events. It can provide us only with a partial ordering of events. For example, if we ask ourselves, in the same example that I gave before, if we ask what is the relationship between B, which is this event right here, and D, we have no information according to the conditions that we have provided. We have no information how B happened in relationship to D. We know other relations, A and C, C and E, B and E, but we have no information between B and D. So therefore we say that the relationship has happened before. Until now it's a partial ordering. In order to fix this and give a total ordering, we introduce the logical clocks, which is an important concept introduced in Leslie Lamport paper. Now, logical clock, in order to have logical clock, we should have the following condition. If A has happened before B, then C of A is smaller than C of B. C of A is also it's the timestamp of A in where A happened, and C of B is the timestamp of B. Now, in order for us to have a logical clock condition or a logical clock concept, we should have the following two conditions as well. If A and B are events in process Pi, then A comes before B. Then the timestamp of A should be smaller than the timestamp of B in the same process. But if A is a sending message from Pi and B is the recipient of the message, then Ci of A should be smaller than Cj of B. Those come also from the conditions that we introduced before in the relationship of ordering of events. So this is the logical clock concept. Now, in order to implement the logical clock, we should have some implementation rules. Each process Pi increments its clock Ci between two consecutive events. In order for those events to have different timestamps, then this process should be incrementing the clock or the timestamp that it gives to the next event between those two consecutive events in order for this relationship to be valid. Now, if A is the sending of a message M, is sending a message M by Pi, then M includes a timestamp. So when a process sends a message to the other process, in that message it should include a timestamp, which is Tm in this case, and it's equal the same as Cia. Now, in order to have a relationship has happened before, and in order to have the logical concept, then when Pj, which is another process, receives the message M, it sets its clock to a value greater than or equal to its present value and than the Tm. So, for example, if another process J receives a message from the other process I, then it should receive the timestamp of that event, and it should assign this event a higher timestamp than what it received. So, in order for us to say that process event A happened before B. Now, we have provided those concepts in order to define a total ordering. While defining a total ordering, we can have synchronization, we can solve synchronization problem in the distributed systems, and we can also avoid the deadlock concept as we learned in the class. We can define a total ordering on the set of all system events as A happened before B if either one of those conditions is satisfied. So we can say A happened before B if Ci of A is smaller than the Cj of B. Or we can also say that A has happened before B if Ci of A is equal to the Cj of B and Pi is smaller than Pj. Keep in mind that the Ci of A and Cj of B are the timestamps of A in process I and B in process J. This will help us defining a total ordering of all events in a distributed system environment in order to accomplish synchronization problem or avoid deadlocks. Now, by seeing this, we can also see that there are some anomalous behaviors in logical clocks. These anomalous behavior, they happen in the presence of outside interactions. So, for example, if two processes are happening in a distributed system and they are dependable on a diskette, what happens if we transfer or if we carry a diskette from a machine to the other one? Or what happens if the dictating file change, if we dictate into another process over the phone or something like that? So those behaviors will, anomalous behaviors will happen. So for example, here we can see that if A is sending a message to C, and C, before it receives the message from A, sends a message to D. Now the question is that what is the relationship between A and D? We might not know in this case because A sends a message to C, and before C receives that message, it sends a message to D. So we are not sure what is the relationship between A and D. So in order to have a total ordering of all events in a distributed systems, we're going to have a strong clock conditions, which is defined in the following way. We're going to let S be the set of all system events, the system events that are internally, plus the relevant external events that are happening outside of a process. Then we can say that for any events A and B in this all system events S, A has happened before B only if the timestamp of A is smaller than the timestamp of B. Now by saying this, by satisfying this condition, by this strong clock condition, this will provide us a total ordering of events in a distributed system. This was also the concept that we wanted to introduce in this paper. By satisfying the strong clock condition, we can say that we have provided such condition that gives us a total ordering of events. This brings us also to the end of the paper and concluding all what we have said until now. So the paper introduces the concept of a logical clocks and abandoning the concept of a physical clock. This paper describes an algorithm of extending partial ordering to a total ordering through the strong clock condition and logical clock concept. By using those two concepts, we're able to total order of the events. This then can be used to solve synchronization problems in distributed systems and avoid deadlock situations. Thank you very much for watching this video, and please, if you have any questions regarding this paper, send me an email at nkaja@umich.edu. Thank you.